Now we'll come back to the pressure measurement topic, the pressure, how to measure. Whether we are measuring the gauge pressure, vacuum pressure, or absolute pressure, we will see about it. So in the case of the gauge pressure measurement, if you want to measure the gauge pressure of a point, let you take here, one pipe is there. From the pipe, we are connecting this manometer. We want to finding out the pressure of this pipeline. In that case, if you want to finding out the pressure, so with respect to atmospheric pressure, you are finding out. Because it is open to atmosphere, this side of the gauge is open to atmosphere. So whatever the pressure you will get here, that is with respect to atmosphere. So whether the pressure may be the gauge pressure, or this may be a vacuum pressure. Because as it is, this side is open to the atmosphere, whatever the pressure you are getting, that may be either gauge pressure or vacuum pressure. So to get the absolute pressure, you have to plus or minus with the atmospheric pressure. Then only you will be able to get the, because here as it is open to atmosphere, so atmosphere is a reference point here. Reference. So due to the pressure A, here in case of the manometer, we are using one manometric fluid. So previously the fluid was in this way. The manometric fluid we are using here. So how it was looking like at the initially, as no flow through the pipes. So as there is a no flow through the pipe, so initially the manometric fluid was in the same level. Here it is a manometric fluid. Initially it was like this. Because of the hydrostatic paradox, it was the same level initially. Because this side also open to atmosphere, no flow, no water flow. Here also open to atmosphere, so both sides is the same pressure, so it will maintain the same level here. And obviously, it may be the liquid in case. We are considering here for the case gas also will be used, so it is not invariant. So manometric fluid was like this. Now the flow started through the pipeline. So we are going to finding out in the pipe a point what is the pressure. So as the pressure, the PA is more than the atmospheric pressure. As the pressure is more than atmospheric pressure. So what will happen? This will create more pressure. This liquid will create more pressure over this column and it will goes up. Because it is PA is more than, because that side atmospheric pressure is also come. PATM is come. But PA is more than PATM. So that is why it will suppress more. Here, this fluid is known as the manometric fluid. In the manometer we are using, so this fluid is named as the manometric fluid. Mostly as a manometric fluid, we are using the mercury, sometimes water, air, so many things can be used, etc. So here, after that, what will happen as the pressure PA is more than the P atmosphere? So what will be happen here? That side there will be suppression. So if you draw this thing, here if you draw it because of the pipe PA, so this side level will getting down, this side level will go up. It will be in this way. Just for the sake of the understanding, I'm telling. This side will be level up. So in such a condition, because the pressure here, PA, is more than the P atmospheric pressure. And the difference will indicate the differential head will indicate how much this pressure is greater than the P atmospheric pressure. So if you write down the equation in here, in this kind of the problem, PA, let you take this PA, this height from A point to this height, you cannot consider also it's a invariant, but if you consider it as A, both side, if you consider it's A also, it does not affect, because PA here, whatever the pressure is coming, that is also let you take PA. This height, if you consider as a hydrostatic height wise, you can consider from the PA up to this, but it does not matter. First of all, in such a situation, you have to choose one reference line, where in the reference line, if you consider here in the just this line is the reference line. The horizontal line, x dash now a reference line. As it is a reference line, so about the reference line here, whatever the pressure is at here also the same pressure. How it is the same pressure? Because if you consider here that this height is, this is the A. So PA, if you write down the equation PA at the point of the A is the point at here, PA, as it is going downside, this liquid might be some working liquid, W, working liquid, and this liquid is a manometric liquid. The density is the rho m, here the density is the rho W. So these two different density. Here the density is the air. It is open to the atmosphere. It is open to atmosphere, density of air it is there. So in such a case, if you write down the equation in this way, so what will comes? This A is invariant here, but still we are taking care. So rho W, A plus H, G. This is the pressure is over this axis is acting. This much of pressure is acting here. So about this axis, let you take this height also B, some B. So if you go from this point downwards, so downward, whenever you are going downwards, you have to plus. If you are going upwards, you have to minus due to the hydrostatic. Already you have seen this equation dP dz is equal to minus rho g equation, the hydrostatic law by this one. So in that case, if you go downwards, so what will comes? Rho m b into g. You come here. Again you go up. So rho m b g. The same pressure. So it is cancelled out. So it is better to be here, and here is the same pressure, we can tell. Then you go up again. So how much it is? Rho m h g. Rho m h g. Then it is open to the atmosphere. This is the open to atmosphere. So open to atmospheric means here the atmospheric pressure. So already you reach the where the atmospheric pressure is kept. So it is nothing but is equal to P atmosphere. In this way, you have to establish your equation in this way. For the, and whatever the PA will get here, this PA should be greater than P atmospheric. PA should be greater than P atmospheric. So as it is a PA atmospheric, in terms of the H you are getting, this PA minus P atmosphere or gauge pressure you will be able to see. The gauge pressure you will be able to finding out from this equation. So that is the manometer. From the manometer, I will show you how to get the gauge pressure. In the manometer, how to get the vacuum pressure now we'll see. So let you take here, it is under vacuum. PA is, in this condition, PA is less than P atmospheric pressure. So that means atmospheric pressure is more than this pressure. So initially, both are in same level, let you take. Manometric fluid, both are in same level. Initially, both are in same level. Now what is happening? So as it is a vacuum, so this way, manometric fluid will goes up. There is the initial condition, and this way it will getting down. So manometric fluid, because of the vacuum, as there is a vacuum, so manometric fluid will go in this side, in this side. So this would be the condition. So now this will be the reference line. This will be the reference line x-axis. So whenever the reading you are getting in this way, so you will get the vacuum pressure. So in that case, the calculation, if you do it, PA should be less than P atmosphere. So vacuum pressure. So hence we can conclude from the manometer, we can measure gauge pressure. We can measure vacuum pressure. So both pressure we can be able to measure by the manometer. U-tube manometer. As it is looks like a U, so it is named as the U-tube manometer. Simple, better to write it in this way. Simple U-tube manometer. If this U-tube manometer is measuring the differential pressure, so you will tell that differential U-tube manometer. Nothing is in there, just we'll do the calculation, but for better understanding, U-tube manometer can measure gauge pressure as well as vacuum pressure. It can measure the pressure of the liquid. It can measure the pressure of the gas. It can measure the pressure of the liquid. It can measure the pressure of the gas. Instead of here, water, if there is some gas, working fluid is a gas, it can measure. So it does not matter for the liquid or gas. As there is a sufficient one manometric fluid, so this manometric fluid will mix the level and show you what is the pressure. So this is the most unique type manometer. The most simplest manometer form is the piezometer. That is the most simplest form. The simplest form of manometer, piezometer. We are going to find out the pressure at here, PA. So PA. So one tube is here. This tube, as the pressure PA is more than atmospheric pressure, what will be happen? As it is a more than atmospheric pressure, so PA is more than atmospheric pressure. Outside is the atmosphere. So atmosphere, here the pressure is more less pressure. Here P is a more pressure. Due to this, if you include one tube here, so some level it will take. Some level it will take. Is the level it will take. And this level will dictate how much pressure difference. The simple type of manometer is a piezoelectric piezometer. We are telling it, not electric, it's a mechanical type. So here you see it takes the height of H. What is that H? If you come and measure this thing, this height it has taken as a H. Better to write it from here rather than. x the height of h. So here if you write down the equation, what the pressure is acting here, that is the atmospheric pressure. So atmospheric pressure plus h into rho of working liquid rho W into G. That will be equal to the PA, pressure at A. So P atmospheric plus H into rho WG is equal to PA. Hence you are getting PA minus P atmospheric pressure divided by rho WG is equal to H. So whatever the height you are getting, that is due to the gauge pressure head. That is due to the gauge pressure head. So in the piezometer, you can only able to find out the gauge pressure. So gauge pressure can be measured, but vacuum pressure cannot be measured. Because if there is a vacuum, so no level will be formed here. No level develop from the level. Only level is sensed here, and this level is showing the pressure difference. So vacuum pressure cannot be measured by the piezometer. Previous case, the manometer cases, you have seen both gauge pressure and vacuum pressure can be able to measure. Next thing is only liquid. Why it is only liquid? Because if instead of liquid there is some gas, so gas will not make any surface. Gas will not making any surface here. So you could not be able to measure the height. So only liquid can form the surface. So that is why. So only liquid can be able to measure by piezometer. Next thing is if this PW is very low, if the PW is very low, the density of the liquid is low enough, then the height will be more, H will be more here. So, because if you decrease this thing, if it is a low, so height will be more. So to accommodate this height, the pipe height will be much more. That is one drawback. So the moderate density can be measured. Low density fluid cannot be measured by this. Next thing is if the pressure, gauge pressure is high enough. If the gauge pressure, it is high enough. It is high enough. 140 bar. In such a condition, the amount of the height of the liquid should, so how much bigger pipe you have. So high pressure, to measure the high pressure is very difficult. Because if I want to make 140 bar and it is a water, so how much height is required to measure this thing? Because you know 10.4 meter of water is equivalent to 1 bar. So to measure 140 bar, so 140 times of the 10 point. So 1400 nearly meter of pipe you have to give to measure this thing, to the piezometer. So high pressure measurement cannot be done. Moderate pressure or medium pressure can be done. So we can able to measure the moderate pressure. The previous example, the manometer, you could be able to get the high pressure. High pressure you can measure, low pressure you can measure, high density fluid you can measure, low density fluid you can measure, liquid, gas, everything can be measured by manometer. But the scale should be proper. You have to choose your manometric fluid in such a way. So YouTube manometer, we have already discussed about it. drawback in the YouTube manometer, there is some drawback is there, YouTube manometer, that is but we'll just once more we're talking about the YouTube manometer in case of the differential fluid. Differential YouTube manometer. If you want to find out the differential pressure to the YouTube manometer, is possible. Take 2 points here. Same pipe line is the same pipe. Let you take 2 points you are measuring here. One YouTube you are choosing. Point A and point B. The same pipe. You consider one pipe. For the pipe, same point. This looks like this. Point 1, point A, or point B. We are going to now finding out the differential pressure between 2 points. How to finding out? From the formula we'll see it. Then we'll comes here. So here 2.0. This point is the A. This point is the B. So let you take here the PA is greater than PB. So as the PA is more, so that side the manometer depression will be more, that side the manometer depression will be less. So that is the manometric fluid, PM. Rewrite this equation, why it is. Better understanding will give you total distance from here to here, that you get A. This depression is, manometric fluid depression is H. A and B at the same height. If it is not same height, we will consider in a different manner, but that you take here is the same height and same fluid is there. So rho W, the rho M. It is not open to the atmosphere, so differential pressure we are going to measure here, not gauge pressure or vacuum pressure. In this kind of, it's a differential YouTube manometer. Case is the differential YouTube manometer, not one side open to the atmosphere. Consideration is the same. So PA plus A is the height, rho W into G. That's height, the pressure. The reference line is now choosing at here, X axis. So at here, what about the pressure? Here also the same pressure. Because if you go down and come back, it will be neutralized. That will be equal to, it will be equal to the PV plus this distance A minus H rho WG plus H rho mg. That is the equation. We write it down, the manometric equation, in this way. In this way, you can write it down, or separate way also you can write it down. But the sense is the same. You come from this point to down up to here, from similarly in this side. So left limb you come from here to here, right limb also you come from here to here. So PA plus A rho WG. On the other side, PB plus A minus H rho WG plus H into rho mg. So already A rho WG will be cancelled out from the both sides. PA minus PB will gives you H rho mg minus of H rho wg. So hence you take H rho wg is as a common rho m by rho w minus 1. This will gives you the equation. So the pressure head you will get in this way. So whatever you are getting this manometric depression, if the manometric depression is given to you, you could be able to get the pressure head. If you take the same equation, the A point in this consideration, what is the consideration? A and B are at same horizontal location. A and B are at same horizontal location. This kind of the consideration we have seen it. If A and B are not same horizontal location, in that case, let you take A location is somewhere else, B location, both are not in horizontal, but depression is showing the same. In that time, you can write it down rho A plus rho G ZA minus, PB, PA plus rho G ZA minus PB plus rho G ZB is equal to the same equation you could be able to write it. If your depression is the same. What is that? Rho A plus rho G ZA and rho B plus rho G ZA. This is known as the piezometric pressure. EA star, we can write it down in terms of PA star minus PB star. That is the piezometric pressure. PA star is the piezometric pressure, and PB star is also the piezometric pressure. What is that? A by rho W. Whereas this PA star is equal to static pressure plus, because of the height difference, potential head difference, what is the pressure? This combined it is told as the piezometric pressure. So both the case, if the depression is the same, both the case it is the same. If both points are horizontal, so ZA is equal to ZB are the same. Both points are horizontal, so ZA and ZB are the same. So this will be cancelled. Pressure will come. If A and B are not the same point, it will come under in this way. So this is the consideration for the differential ED manometer. Next, we will see the types of the manometer. There are one types is the micrometer. Micrometer, or it is known as the well type manometer. Well type manometer. Well type, this portion is a reservoir or well. It is known as the this reservoir or well. Why we use the reservoir or well? We'll see it. To get the fine pressure measurement. To get the fine pressure measurement. Let you take here one fluid was there. One fluid was there. In this way. Okay. Both are in the same level initially. Both are in the same level. Micro-Manometer, we'll see some example. Same manometric fluid or some fluid is here. Manometric fluid. Now some pressure is given here. Some pressure is given here. Let the pressure is the PA. Some pressure is given here. Because of this pressure, this side, the PA, which is given here, is this side is open to atmosphere. So PATM. So here some depression will be taking place. This level will depressed. So initially the level was here. Now the level came here. Initially level was here. So del H level depression has been happened here. As this diameter is more, A, let you take the area of this part. We are taking the area of well. And here the tube area. A is the tube area. So here depression is del H. But because of this amount is coming down here, it will be more. Here the height will be some more height that you take H1 height. This way. Here del H reduce, but due to this here H1 height is increased because the diameter or area is less for the tube as A is greater than small. Well, area of the well or reservoir is more than the area of the tube. That's why. So in such of cases, first of all, you have to write the continuity equation. Continuity equation. In this case, continuity equation means how much it is coming down, how much amount, and how much it is going up. So the volume is coming in the left arm limb, the volume A into delta H. It is getting down. A into delta H should be equal to the small a into H1. That is the continuity equation. We can be able to write it down. So delta H, we are writing here A by cap say into H1. Now, again, we have to go for the manometric equation. In case of the manometric equation, you have to choose the reference line. As here the same liquid is there. Liquid is not changing here. Same liquid. Now the only height is rest, but liquid is the same. If you take it's the rho A manometric density of the liquid. Previously also it is the rho A. In such a condition, how much height is getting up? H1 plus delta H. Now direct you write down the equation. Here the pressure comes. What is the pressure comes? PA. Because of the PA pressure only this depression is occurring. So PA, here it is acting only PA. That should be equal to the PA. That should be equal to this height. And what is that? Rho M G H1 plus delta H. Rho AG H1 plus delta H. That should be equal to plus atmospheric pressure. That is the atmospheric pressure. So because of the PA pressure, one more thing to be taken out here. PA pressure is acting here. In the right side, in the left side, you have to write the equation. This equation is not correct equation. We are again writing this thing for this purpose because it is not correctly came. See here, PA is acting at here. Still further it is down by delta H. So PA plus, now the working fluid is rho W. So rho W G delta H. That is the pressure at here in this point. In this point of pressure, P atmospheric pressure plus rho M G H1 plus delta H plus only this. So that is the equation. So in this equation, PA minus P atmospheric pressure, be able to write it. Manometric pressure G H1 plus rho M G del H minus rho W G. Hence here GH1 plus, in that case, if you take the common here, G is the only common term, G delta H. So delta H into G rho M minus rho W. Now you put the values of the delta H here. Delta H, you could be able to write it down. Rho M G H by A H1 G rho M minus rho W. That is your equation. So this kind of the equation, it will come here. If your A by A is much more less than 1, much less than 1, so you can neglect this term. You need not to consider this term. So in that case, as you need not to consider in this term, so here you could be able to simply write that the pressure difference is nothing but is equal to rho M G. Simply you can write it. So the micro-manometer concept, how much depression is happening in the well or reservoir. On the other side limb, there is a small tube. So why we use this concept of micro-manometer? Because very small pressure we can measure by micro-manometer. What is the advantage to take this micro-manometer? Because manometer is able to use. Now we'll see. Apart from this, all calculation is easy here. But what is the use of it? Small pressure difference can be measured. Because with the YouTube manometer, if you see the YouTube manometer, small pressure difference, because if the pressure difference between PA and PB, in this case, if it is very small, so H will be less. If the H will be less, so you cannot see. If H scale is very less, you could not able to see. So, because this measurement, you have to measure it. If it is beyond 1 mm, you cannot measure. If the H is less, very much less amount, so there might be some error, measurement error will come. So you have to get this H, you may reduce the working this way. This difference you can less. Manometric fluid density you can able to reduce. But it chooses on different way. But here in the differential type or micro-manometer, in this concept of the micro-manometer, if the pressure difference is small enough, you can see here the pressure difference is small, but here you can see on the other hand, as the because of the area difference on between the reservoir and the tube, you will get the sufficient height to measure this thing. That is the advantage here. One more thing is the inclined U-tube manometer also. The inclined U-tube manometer, there is some use here. It's just a inclination is there. What is the concept here? The concept is the same, similar type of the concept here. If you take one point, same thing I am just doing repeatedly. Here the point you take A, and from the A, initially the level was here. Some initial level you can choose here. Take here some initial level is here. Was the initial level. Now because of some pressure, there might be some depression. Final level is at here. So that you take here, it is the final level. Initially it was. So here how much depression is happening? Delta H, the same way. Inclined manometer. As this is the inclined, here the rise will be more. Here rises. The rise is at here. Initially it was at here. Now the rise is at here. Okay. Height is H1. This is L1. And the angle, this angle is theta. As it is inclined, so angle is the theta. So inclined type U-tube manometer, if you put the continuity equation similar way, just like previous, if you put first continuity equation. So how much depression here? The well area of the well is A, and tube area you are taking as small a. So continuity equation here, right side A into delta H is volume is reduced in the right side, and left side small a into L1, not H1, L1. What is L1 and H1 relation? That's the first continuity equation. Now we'll write it down, L1 and H1 relation. What is the relation here? So this is the L1. So H1 by L1 is equal to sin theta. H1 by L1 is equal to sin. So L1 will get you H1 by sin. Now nothing is there. After that, you just write down the manometric equation. Manometric equation, this density of this here, it is the same way. It is the manometric fluid, rho m. So the density in this way, PA in this side plus your reference line is now at here. It's your reference line. So PA is acting here into delta H, working liquid into J. On the other hand, P atmospheric pressure plus rho m G H1 plus delta H. What is the H1? H1 is L1 sin theta. L1 sin theta into delta H. Delta H you will be able to get from the continuity equation. That is, can be written as the delta H is equal to A by small a into in terms of A. Here you could be able to, from the scale, you could be able to get L1. L1 you could be able to see here. As you are getting this L1, you will be able to see the L1, your scale is rising here. Because the sine theta cannot be greater than 1. Sine theta is always less than 1. So as it is the less than 1, so L1 must be always greater than H1. So your scale for the observing the scale is rising. If you make one side inclined condition, so the scaling is more. By this way, you could be able to get the pressure difference formula. So PA minus P atmospheric will come in this way. If you take this A by this small a is much less than the capital A, then you can cancel out this term. This two term you can cancel. The remaining term will gives you the inclined pressure measurement. So this making the tube inclined, invoking the well or reservoir, it will gives you the more opportunity to measure how sensitively we could be able to measure, how much precisely we could be able to measure the manometer here. Another thing is the inverted tube manometer. Inverted tube manometer is also, here also it is for the gas pressure. Let you take some gas. Gas is some gas is inside. We are going to measure in the pipeline, there is some gas is flowing here. Point A is the point B. In such a cases, we are going to, or very much less difference, PA and PB, difference is very less. It's nearly equal, very less difference. We are going to find it. To find in such a cases, inverted tube manometer is most useful manometer. Inverted type. Because to keep the inverted, there is as a manometric fluid, whatever the manometric fluid you are using, the density of the manometric fluid is less than the gas density or working fluid density. What I'm telling, repeating, the manometric fluid density is less than the working fluid density here in such a cases. So that will give you the advantage to finding out. It will give you the advantage because as you decrease the density of the manometric fluid, you will get the more precise height. This height will give you the better way. What is the condition?